Okay. Yeah. So like I said, we're going to go ahead and pull this NeuroPython Docker, just so I can kind of show how it works. But if we just look at the GitHub repository for NeuroPython, you can see that there's a directory here for documentation. There's a directory called Docker. I'll come back to that in a second. And then there's the NeuroPython directory, which actually contains all of the Python source code. And then there's some other files related to git ignore and testing and stuff. But you notice there's a Docker file here. And it's in just the root of the GitHub repository for this library. And then there's also this file down here called dockercompose.yml. So if you're not familiar, YML files are short, they stand for YAML files. I think YAML stands for yet another markup language. Yeah, okay. So YAML is essentially a version of JSON, or it's an extension of JSON objects. It's a very simple format that's easy to read and write for humans. And so it's kind of a nice file to write configuration file, or file format to write configuration files in. And we'll look at that in just a second, but I'm going to start by looking at the Docker file.
Sorry to interrupt, but could you share your screen?
Oh, I'm sorry. I thought I was sharing my screen.
No worries.
Thank you for reminding me. Oops. Here we go. Okay. So sorry, since I wasn't sharing my screen, I'll just go back to the root for a second. So we have here a Docker file and a dockercompose.yaml in the root of the NeuroPython GitHub repository. If you want to go to this website, it's github.com/noahbenson/neuropython. Yeah. YML, usually, sometimes those end with YAML, and it stands for yet another markup language. Okay. So if we go into the Docker file, you'll notice that the very first line, remember when we were doing Docker, we started with from Alpine, which is a very, very simple little Linux distribution. We used it because it was small. You could download it. It's just a few megabytes basically, and we used that as the basis for our Dockers. I guess yesterday or the day before when we did the Docker lesson. The NeuroPython Docker starts from Jupyter/SciPy notebook, and basically what this means is that the Docker image that I build the NeuroPython Docker from is already in a Linux distribution that has installed Jupyter and SciPy and NumPy and a whole bunch of other scientific utilities. This is sort of their data scientist notebook, and you can actually use it. You can just Docker pull Jupyter/SciPy notebook, and you can start it up, and it'll start up a Jupyter notebook inside of your Docker, and you can connect to it using a web browser. Now, connecting to something inside of a Docker container isn't something we talked about yesterday. It basically runs like a web server, and you can connect as if it were like an alternate server on your network or something. You have to tell Docker about that, and I'll talk a little more about that later. So here's a line we didn't see yesterday. I'm just noting that I'm the maintainer. And then I've got a bunch of run statements, which basically go through and install a bunch of things. We're installing libraries like nebabble. Sorry, this is kind of small, isn't it? Let me make that bigger. So nebabble, if you're not familiar with it, if you're not familiar with nebabble, nebabble stands for neuroimaging Babel. Reference to the Tower of Babel. It's the library that speaks all the neuroimaging file formats. That's the kind of idea there. So it's a library that can read in Nifty files and FreeSurfer files and Human Connectome project files and all that kind of stuff. So these are just some installation lines. We haven't talked about Conda, Anaconda, or Miniconda. It's another Python installation tool, but I'm just going to kind of gloss over that for now. There's a bunch of kind of setup. We're setting up some Jupyter things in this Docker file. There's a few copy things where we copy a few important files into the Docker. But basically, all of this kind of boils down to this Docker file is doing a bunch of what looks kind of complicated, but honestly is just some fairly simple Linux operations to install NeuroPython inside of this Docker image that already contains a Linux distribution and a Jupyter notebook system and SciPy and a bunch of the other libraries. Then there's a little bit of a few downloads a few data files that NeuroPython uses on occasion. Most of this is not all that important, to be honest, so we'll just kind of gloss over it. But down here at the end, we have this entry point where it runs this main.sh script. And that main.sh script basically just starts up a Jupyter notebook when you start the Docker. So this is a real Docker file. This is one that I use for NeuroPython and that people around the world use to build the NeuroPython Docker and run it. Now let's look at the Docker composed file. So this file has a very different format. And the purpose of the Docker compose file is to basically describe how you usually run your Docker and how you both build and how you usually run your Docker. So recall that when we wanted to run a Docker image as a container, we often had to use this very long, ugly command line. It was like docker run --rm -it -v, some path colon some internal path, then the name of the Docker, and then command line arguments. And for someone who's never used Docker before, it's a little bit intimidating and it doesn't really mean very much. A lot of those arguments aren't really obvious what they're doing. And that's kind of a problem. It used to be that I didn't have this Docker compose file in NeuroPython, and just about once a week I would get an email from someone asking what had gone wrong when they were running Docker to use NeuroPython. And usually 9 times out of 10, it was that they had just slightly messed up the command line. So what Docker does is it simplifies a lot of that. So I'll start by just kind of walking through this Docker file, and then maybe we can look at a couple other simpler examples, or maybe possibly look at how you would use this. So this first line just says version 3. That's actually the version of the Docker compose YAML language. So pretty much 3 is the only value I've ever put here, but there's different, basically Docker compose started out with a particular format for its YAMLs and they updated it a few times, and this is the current version, version 3. Then we have this services, and you notice that everything beneath services ends with a colon and everything beneath it is indented. So all of this is all about what Docker compose considers services. And services are basically individual Dockers that you want to start simultaneously. So the reason that this is the way you specify this and not just, hey, here's the Docker I want to start, is because Docker compose was really made for people in the tech industry who are like working at somewhere like Amazon, and they need to start up a whole bunch of SQL servers plus some web server plus some whatever else they're running, some cleanup routine, all simultaneously, and they all need to work interactively. And not only that, but they probably need to spin them up elastically. So when traffic on their website gets higher, they need to spin up a whole new web server and a whole new SQL server and a whole new whatever other routine going with it. And they need to be able to do that very efficiently. And the idea is that you would build a Docker that ran a web server, a Docker image, and you would build a Docker image that contained your SQL server, and you would build a Docker image that contained whatever else. You would give them all access to the same piece of the file system using the volume mount, and you would start them all up simultaneously so that you had all of your services kind of running together. The way I use this in science, and the way most people I know use this in science for reproducibility, you only really want to start one service at a time. You don't typically want to start a whole bunch of Dockers. I'm just kind of giving you some history on why it's done that way. Any questions so far? I'm just kind of blabbing, so stop me if there's anything you want to know more about or anything that doesn't make sense. Okay, so then we have this NeuroPython here. So this is the only Docker image we actually want to start up. This is the only Docker container, I should say, that we want to start up in this Docker compose file. And the first thing we say is we want to build a Docker from the current directory. That's what this dot means. So recall that when we did Docker build, the way we ran it was Docker build, and then we gave it the directory we wanted to build, which was dot. And sometimes we gave it a tag. And you can if you want, you can actually have this build colon be multiple indented lines after it. You can put things like a tag, but for NeuroPython, we just are telling basically the Docker Compose file that when we start up our Docker Compose system, we need to build the NeuroPython Docker using the current directory. And then I'm going to skip over ports and environment for the moment. We'll come back to that. Environment is actually just environment variables that you want to send to the Docker. So that's very simple if you're familiar with operating system environment variables, but they're not super important for the purposes of this material. But volumes are the equivalent of that -v command line we used, where we could take a directory on our computer and have it be inside the Docker, so the Docker could read stuff from it and write stuff to it while it was running. And basically, the way this works is exactly the way it works on the command line, where you put the directory on your local computer and then a colon, and then the directory you want it to be mounted on inside the Docker. And as a good example here, I'm just curious, how many of you use FreeSurfer pretty regularly? Okay, so some of you. So anyone who uses FreeSurfer probably recognizes this subject stir environment variable, because FreeSurfer, when it was written back in the 90s, I think they probably thought it was the only program you were ever going to have that would have a subjects directory, and so they said that their environment variable for a subjects directory is subject stir. So when you're using FreeSurfer, you typically set this subject stir variable to be whatever directory you have your FreeSurfer subject stored in. And so what this line basically says is, you know, if the user, whoever starts up this Docker, has defined the subject stir variable, take that directory and put it in /data/FreeSurfer subjects inside the Docker. And that's exactly the way we would call it on the command line. We just have a -v before that. Let me jump back to the command line here and see if this finished. All right, it finished. So what I mean by that is we would have run something like docker run -rm-it, and then we would say -v subjects dir :/data/fsaverage. Whoops, FreeSurfer subjects, etc. That's how we would formulate the command line. So here, basically, what I've managed to do is I've managed to put that piece of the command line into the Docker Compose file. So the way that this works in practice, so let me, I'm going to go to my desktop and I'm going to git clone. Oops, https://github.com/noahbenson/neuropython. That's going to check out NeuroPython here. NeuroPython has a couple data files in it, so it takes more than just a second. I'm going to go into the NeuroPython directory, and there is this Docker file here. So if I wanted to, I could Docker build with this Docker file. And that would require me knowing a little bit about how I wanted to build it, some of the command lines. But instead, what I can just do is run Docker compose up. Docker compose is a command that is built in as part of the Docker system. So it's if you have Docker, you have Docker compose already. And when you say up, what you're saying is I want to start up whatever services are defined in the Docker compose file. So if we type this, basically it's going to automatically do all the build. It's going to download whatever it needs. I mean, we'll see. We'll see how fast this goes. It may take a little while to build, but all of this will build, and then it will run the Docker all without us really having to do anything. It'll put all the volume mounts that we need inside of it, assuming we've defined our environment variables correctly. And it'll start up a little notebook server, and we'll be able to connect directly to it, and it'll be running inside of the Docker image. And that all can be accomplished with that one command, Docker compose up. So that's the basic idea of how I use Docker Compose most of the time for reproducibility. It's mainly a way to make it really easy and straightforward how to define your Docker images. Did you have a question? Sorry, say that again. So what the question was, what environment file is Docker Compose using? So you can put a .env file in this directory and it will automatically read that in and take environment variables, but otherwise the environment variables just come from your current environment when you run the command. So in the shell, just whenever you're running a shell, you have a lot of environment variables defined all the time, and those are just the ones that you get. Yeah. But you can also, you can absolutely put particular environment variables in that .env file. And in fact, I think I do use some of those for NeuroPython. Yeah. Any other questions? Okay. All right. Well, this is still going. I think this is maybe a good place to stop for Docker Compose, unless you'll have more questions. I guess, well, I guess we have a whole hour, so maybe I don't need to rush through this. So I can show you another example of how I've used this, although once again, it will probably, I didn't build any of this ahead of time, so any Docker image we run that's real will probably take a little while to run and build. This will, I'm going to guess this is about 10% of the way done at this point. Okay. So I'll go ahead and show you another example. So I don't actually remember what this repository is called, so let me check. Nope. So I have somewhere, so in your, it's actually in the NeuroHackademy curriculum. That's probably the easiest way to find it. Okay, so can't see anything there. Okay, so if you go into the Benson Docker NeuroHackademy curriculum, there's also a Docker file and a Docker Compose in here. Actually, there's no Docker file. There's just a Docker Compose. So this is another kind of use case. Now, the contents of the Benson Docker lesson, if you took a look at them on in the NeuroHackademy curriculum for this year, are not really readable if you just browse them. So you'll notice there's some things here. There's this Docker intro directory, and it contains some stuff. There's a Docker file in here, but this is largely lesson contents. There are actual markdown files that describe the lessons and stuff, but they're not very easy to read and they're not easy to navigate. This particular directory doesn't really contain stuff that's meant for you to just read. It's rather contains everything you need to run a web server that will show you that stuff. So this is still running. I honestly think this is going to take too long, so I'm just going to cancel it. I'm going to instead, I suspect that this curriculum directory will build rather fast. So let me go ahead and git clone NeuroHackademy 2022-curriculum. So I'm just going to clone the curriculum for NeuroHackademy to my desktop. Okay. Apparently, the NeuroHackademy curriculum also contains some data files. There we go. I'm going to go ahead and go into that directory, and I'm going to go into the Benson Docker. Okay, so we can see that we have our Docker Compose file here. So let's just cat it to see what's in it. It's very short. Once again, we have this version 3 line, because this is still the same version 3 of the Docker Compose format. Then we have this this myJekyll server. That's the only service that gets started in this case. So on the other Docker Compose, this was NeuroPython : because we were starting up NeuroPython, but what this Docker compose file starts up is what's called a Jekyll instance. So Jekyll is I think it's written in the language Ruby, and I think it's for, pretty sure it's written in Ruby, and it's for running these very simple websites that are made out of Markdown files. And basically all it says is, yeah, here's the Docker image you want to download. You notice this is like a Docker Hub Docker image name that we could pull. So we can go ahead and, for example, Docker pull that particular Jekyll.
Noah, can you hear me now?
Yeah.
Yeah, the question I was asking really is, when you executed Docker compose up, was it using the environment in Docker compose YML or Dockerfile?
Okay, so that's a great question. There are environment variables in the Docker file, and there are also environment variables in the Docker compose file. Okay, so in general, in the Docker file, if you're doing something like you're using the env command to set an environment variable, what you're doing is you're setting the environment variable inside the container when the container gets run. So in a Docker file, like env x equals 10 would make sure that when you ran the Docker container, the variable x was set to 10 inside the Docker container. The Docker compose file, on the other hand, you can set the environment if you want, but generally speaking, and let me go back to the whoops, just so we can look at it. So generally speaking, you can set environment variables in the Docker compose file as well. You can also just use environment variables in your current shell, which is what I thought you were asking about earlier. Yeah. So here we're setting environment variables because this is part of the environment bit of the image or the container instructions. So a tricky little thing about Docker compose is that almost everything you can do on the Docker command line or in a Docker file, not quite everything, but almost everything you can do in a Docker command line or Docker file, you can do in Docker compose. And usually the syntax is a little nicer. So here, I'm just saying that, yeah, when you start up this NeuroPython and when you build it, make sure that the environment has all these things in it inside the Docker image. Down here, on the other hand, like this subject stir will come from your current environment in your current shell when you run it, or when you run Docker compose up. And that's a little confusing. That's just something you have to learn about the way that Docker compose works. It's not like it's just a rule that Docker happens to follow. Does that answer your question? Okay. Any other questions? All right. So we went ahead and pulled Jekyll. We actually didn't need to. We could have just ran Docker compose up once again. So basically, I'll just finish walking through this real quick. When we run Docker compose up, it's going to start up this Docker image as our running Docker container, the Jekyll/Jekyll stable. It's going to take our current directory, which is what $pwd is. So pwd is your current working directory. And it's going to put it at the location /serve/Jekyll inside of the Docker image. Now, the reason it does that is because this Docker image, this Jekyll Docker image, when it starts up, it looks in this path to see if it can find a website. And if it finds a website, it starts up a web server that serves that website. If it basically, before I run this, if we look at the contents of this website, it may not, or sorry, look at the contents of this directory, it may not look like a website to us, but it is a website in the format of Jekyll. And so when we run Docker compose up, notice it didn't have to pull that Jekyll Docker because we already pulled it up here. Okay, it's taking a little while to get started, but in theory, at least, it should. There we go. Okay, so it's doing some updates. This actually may also not be as fast as I'd hoped, but and I'm actually a little worried that it's not going to work because things are now updating from newer versions of Jekyll than when this was all written. So it depends whether Jekyll has changed their formats or anything, but we'll find out in a minute here. Oh, there we go. Okay, so it's running now. And if I go over to my web browser and go to localhost :4000, here we have the contents of that website or that directory as a website, and it's basically just the lesson plan for the Docker lesson. And it ends with this section on Docker Compose, which is the section I mentioned that you can go review if you want some more information about Docker Compose. Okay, did that more or less make sense to people, what I did there? How that all started up inside of a web browser? Okay. Any questions at all about Docker or Docker Compose? Okay, so that's
Sorry, yes, I have one.
Mhm.
In the environment file, I saw that you had a port section and you defined 8888. Is that the reason you were able to access that from the browser?
Great question. Yeah, so in the NeuroPython Docker, I have this ports section here, which says 8888:8888. That may seem a little meaningless if you're not super familiar with TCP/IP protocols. In the Docker Compose file for this, there was a line that said, I think it was 127.0.0.1:4000:4000. That's basically the same idea. But what these mean is that so when you connect to something over a TCP/IP port or a TCP/IP connection, which is TCP/IP is how you connect to websites and pretty much everything, SSH, all that kind of stuff. You always connect to both a computer or like a remote location, an address, and a port number. And the port number is basically telling you which service on that remote location you're connecting to. So typically websites always run on port 80. That's just the universal port that websites always use. You don't have to use that port though. And since 80 is usually used for actual websites, we don't usually use 80 when we're running something like a Jupyter server. We use something like 8000 or 8080 or 8888. And that's what we do here. So what this is saying is that the port 8888 inside the Docker, or sorry, the port 8888 on our computer should be connected to the port 8888 inside the Docker. So when you connect to localhost 8888, what you're actually connecting to is whatever's inside the Docker 8888. Does that make sense to people? That's a kind of weird concept, I think, but that's basically how it works. Okay. Okay, so there's a lot more to Docker Compose, but we're on it. To be perfectly honest, we're reaching the limit of my knowledge of Docker Compose. I use it at about this level pretty often for pretty much every project I do. I have a Docker Compose file just so people can very quickly start up whatever environment I typically use. And I think that's one of the beauties about Docker is that if you're starting a project, like you're going to do a whole bunch of analysis on the Human Connectome project, you can download the Human Connectome project you want to analyze on your local computer. And then you can set up a Docker file for a Docker image that contains like Ubuntu and Jupyter and Python and whatever you need to run. And you can actually do all your analysis inside that Docker image. And you can save it out to your own, to your own computer. And then whenever you're ready to publish your paper, you can just take that Docker image and stick it on Zenodo, where it will be permanently archived and have a DOI. And anyone who wants to come and do your analyses in your computation environment doesn't need to try to worry about getting all the installation corrected stuff. So it's a real boon to people who are trying to reproduce your analyses and your computations in particular. And Docker Compose is a great way to make it simpler for them to start all that up. All right. Any other questions about Docker and Docker Compose? Anything else about Docker people wanted to hear? Okay. Well, let's go ahead and talk about something else then. So if I recall correctly, I want to wait a little bit longer and maybe start talking about Pytorch in like 10, 15 more minutes. So people over there, if they want to come over, have time. But the other popular topics were Git and GitHub collaboration patterns and a little bit more on the Python basics. Let me stop sharing my screen so I can see everyone's votes in Zoom. But if I were going to spend, let's say 10, 15 minutes talking about either GitHub collaborations or about, let's say, Python inheritance and object orientation, people in the room, please raise your hand for GitHub, and people on Zoom, please put a green check for GitHub. And if you would rather hear about the Python stuff, then leave your hand down if you're in the room and put a red X or something in the Docker. Okay. So that was a little bit indecisive, but I'm going to take that unless I hear a slightly more resounding vote in favor of the Python. I'm going to take that as a GitHub vote. Okay, so with GitHub, I need a little help remembering where we left off. So I think we did a pull request. Is that right? But we didn't talk about merging, for example, or we didn't do an example of merging. So I think that's maybe a good thing to show, and I can probably do that in just 10 minutes or so. So let me share my screen again. We'll go to NeuroHackademy.2y2c.cloud. Has anyone noticed any problems with the Jupyter Hub starting up the last couple days since we had that morning where nothing started? No. Okay, good. They told us they were going to try to fix that, so I'm glad to hear it's working. Okay, let me just open up a terminal. Okay, so we were working in this planets directory. The planets directory isn't especially important or anything, but that's I'll just pick up here anyway. The basic idea behind merging. So I mentioned that one of the things GitHub does that's really nice is that when you're editing a file and simultaneously your collaborator is editing the same file, and you both try to check them into GitHub, GitHub is very smart about how it handles those conflicts. So for example, you both edited the same file, you both edited different blocks of code in the same file. Typically Git is pretty good at just saying, okay, these edits don't conflict with each other, even though they're the same file. I can figure out what to insert, and so it'll just resolve that without you having to really worry about it. On the other hand, if you both edited like the same block in the same file, like you both edited the same function, very likely GitHub will say, oh, these changes that were simultaneous may cause problems, and so you need to merge these manually. So the easiest way to demonstrate this is that I'm going to start by opening nano for mars.txt. And I'm going to make a change. And I'm just going to make a simple change. I'm just going to change this to may to might be a problem for Wolfman. So no major change here. I'm going to save that with a Control O and then a Control X to get out. And then I'm going to actually get out of this directory. I'm going to make a directory that's just called temp and cd into it. And then I'm going to clone that planets repository again so that I have another copy of the planets repository here. Now the reason I'm doing this is not for any good reason. It's just, I mean, it's not for a good reason in terms of like my workflow. It's just so I can demonstrate this to all of you what happens when you make two simultaneous edits. So I'm going to clone git at github.com Noah Benson /planets. If you want to follow along, you can use your own planets repository. Did I not set up my Git? Oh, I mistyped GitHub. Not GitHut, but GitHub. Okay. So now I'm going to go into planets here. And of course, mars.txt doesn't contain that change because we haven't committed it or checked it in or anything like that. So I'm going to go ahead and open nano here And I'm going to change this line in a slightly different way. I'm just going to say it might be a problem for the Wolfman. Okay. Now I'm going to push Control O to save and Control X. Now, I haven't committed, added, or pushed either of these, so I'm going to go ahead and do that now. So I'm going to git commit. My message is going to be just edited the wording. And I'm going to go ahead and push that. Okay. And then I'm going to get out of this temporary planets directory I made, and I'm going to go into my old planets directory. So, of course, we haven't pushed any changes. We haven't committed anything here. This is just our scratch kind of area with this change from made to might. But you can imagine if we git pull, it's going to go try to get that change that we just pushed, right? So if we go to github.com /NoahBenson/planets, the version on GitHub now has that change where we added the before Wolfman, right? So if we get pull, it's going to try to sync this version of the file down to our directory over here. But we've made a change here in our file. So Git's going to notice that. So let's go ahead and see what happens. Git pull, error. Your local changes to the following files would be overwritten by a merge. So what it's saying is you haven't committed these changes. You've made a change and you're asking me to overwrite your changes with something that I'm going to pull down from GitHub. And I'm not going to do that unless you tell me for certain that you want those changes to be blown away. Okay, so alternately, it says, please commit your changes or stash them before you merge. Okay, so we can commit the changes. It also says we can stash them. I don't really use stash very often, but I believe it's a way of basically storing it temporarily, kind of like putting it in a scratch space temporarily so you can like work on other stuff and then pull it back. But we'll just talk about committing for now. So let's go ahead and commit. And our message will be that changed may to might in mars.txt. Okay, so now we might want to git push because, intuitively we may not even realize that someone else had changed that file. So I just made an edit, I committed it, I'm going to push it. Oh, another error. Failed to push some refs to GitHub Noah Benson planets. So basically it says updates were rejected because the tip of your current branch is behind its remote counterpart. That's a really like kind of obtuse way of saying your current version doesn't agree with the changes on GitHub. So it says basically you need to git pull before you can push again. So since our current version of the repository, which we've now committed changes to, is no longer matches the version on GitHub, it's there's changes there that we don't have locally. We can't pull because, or sorry, we can't push because that would overwrite the changes on GitHub that we don't have. So GitHub is very careful about making sure that it's not going to overwrite some change you did on accident. It's always going to err on the side of keeping whatever change you've made, unless you really tell it you want to get rid of it. So let's go ahead and git pull. Okay, more information. You have divergent branches and need to specify how to reconcile them. So that's the real problem with the merge. Our two changes were on the same line of the file. So Git is not certain that that it can take one change or the other. It wants us to answer that question for it. So what it's done, some of this message, by the way, is just details of configuration. We can kind of ignore it. But what it's done is, I believe, if we now cat mars.txt, no. Oh, I think maybe I do have to run this. Okay. Yeah. Okay. So sorry. This message here was actually saying this is a bit of a weird message, because what this is really saying is that it used to be that git pull meant something else, and now we've changed the meaning of git pull, and so you have to tell us which version of git pull you want to use, the old one or the new one, by default. So I just basically told it that in this kind of case, I want to use the new version of git pull. for the most part, we can just ignore that. That's just a configuration issue we had to solve. But the important part here is that when we git pull after fixing that, we get this conflict saying that there's a merge conflict in mars.txt. Automatic merge failed. Please fix the conflicts and then commit the results. So if we cat mars.txt, there's a bunch of new stuff in here. You'll notice there's these arrows that say head, and then there's this equals signs, and then there's these other arrows with this gobbledygook at the end. Okay, so let's go ahead and open this up in Nano. What these really mean is that starting with these arrows in the head, this is what we're pulling down from GitHub. Sorry, this is what we changed here locally. This is what we're pulling down from GitHub because this is our head in the current repository. This is the idea of the head on GitHub that we're trying to pull down. And so we have to choose, do we want this version of the line, or do we want this version of the line, or do we want something else? And all we have to do is manually edit this file so that it's sensible again. So I'm just gonna delete all this, and I'm gonna say we're gonna add both versions in. So I'm gonna go down here and delete all this. And basically we can get rid of these lines. And if I want both changes, I just need to add the to that line. I don't have to add the. I could change this line to whatever I want, and Git will accept it. But just going to push Control O to save, Control X, and then we can commit it. Fixed merge conflict. I believe we just git push. No, sorry, git pull. Oh, I believe what I did here. Did I not? Oh, I see what I did. Okay, fixed merge. There we go. Okay, I just forgot to add. Thank you. Okay, and now we can get push, and that'll send it back to GitHub. So really, resolving merge conflicts isn't that tricky. It's just a matter of going into the files that you have the merges in and picking the lines that you want manually. It can be a little bit of a pain, but it's a lot better than trying to fix an actual merge conflict that results from someone overwriting your changes in GitHub or something like that. Okay, any questions about any of this? Okay, so if there are no questions about Git, let's go ahead and talk a little bit more about Pytorch. So my sense from the responses and the just talking to people is that people kind of wanted to hear about convolutional neural networks. Is that am I on base there? Yeah, okay. If there's something else people want to hear about, I'm happy to talk about it, but you'll have to tell me what it is. Feel free to shout out if you want to hear something, but I'm going to assume we're just talking about convolutional neural networks for now. And for this, I actually need to grab a tool. 1 second. Okay, so let's see how this goes as a way to demonstrate this. I'm trying really hard not to use any copyrighted material in these talks so that we don't get in trouble when we share them. So bear with me. So for starters, I just want to kind of explain what image convolution is. So convolutional neural networks typically operate on images, and by image, I just mean like regular ping files, like matrices of numbers, possibly with multiple channels for red, green, blue, and maybe alpha. In theory, this is, here I just have drawn an example of 2 different matrices, which we can consider images. These are both one-channel images. They don't have red, green, blue. They're just a matrix of numbers. The one on the right is a matrix of zeros, ones, and negative ones. So it's not a particularly, it's not a traditional display image or like visual image, but it's certainly an image in that it's a matrix of numbers. And the one on the left is also an image in that it's a matrix of numbers. Now, typically, this matrix on the left, whoa. Not sure what's going on here. All right, I've somehow changed the interface. That's okay. The matrix on the left, we're going to call the kernel, and the matrix on the right, we're going to call the input image. The idea behind image convolution is that you take the kernel image. Oh, I see what I did wrong. Sorry. Okay. You take the kernel image and you line it up somewhere on your input image like this. And sorry, my pencil's not working very well. So you have all these overlapping pixels at this point, or cells, or whatever you want to call them, for the pixels of the image. And for each overlapping pixel, you just multiply them together, and then you add all of them up. So this kernel image, the blue one, has zeros in the first and last column. So all of these values are going to be 0. The input image, the gray one, has zeros in the first and second row, so these are also going to be 0. And here in the middle, we have 1 times 1, and so this is a 1. And so altogether, the sum of the product of these two, of the input image and the kernel for this particular position, is just 1. So I'm just going to write that here. So when we line up the kernel and the input image at this point, sorry, that's not a negative 1, that should be just a 1. The sum of the product of the two images is 1. Okay. And then we go ahead and shift this over, and we do the same thing. And it should be pretty obvious because the input image has rows of 0, rows of 1, rows of 0, rows of -1. It's basically horizontal stripes, and the kernel image is vertical stripes. So this whole row is going to end up with values of 1 as we shift this kernel over and recompute that calculation. And it's not just across the rows, but we're going to also move it down 1 row and redo the calculation. In this case, it's all going to come out to 0, I think. Maybe not quite. No, yeah, it's going to come out to 0. But we'll shift it down, and then we'll shift it over and redo those calculations, and we shift it down again. And we just, for every alignment of the kernel with the input image, we perform this very simple little calculation where we multiply all the pixels together and add them up. That's basically what image convolution is. And although that is the correct notion of what it is, I find it to be a kind of unintuitive notion of what the operation that it's performing is, or why we care about this, or why we would want to use this for convolutional neural networks. The way to think about this, I think, is in terms of an analogy to the visual system. And I am a vision scientist, so I may be a little biased here, but regardless, in the visual system, the very earliest parts of the visual system, that is the retina, they already have filters where your cones and your retinal ganglion cells, they're set up as basically filters on the inputs that you get from your cones and your rods. And they detect things like edges. They also detect things like edges in time, interestingly enough, but that's a whole nother topic. But the idea is that your visual system is basically tiled with tons and tons of filters all across your vision that recognize edges in multiple directions, in any direction. So right from the beginning in the retina, your visual system is already detecting lines and boundaries. And as you get up to higher areas in the visual system, like V1, primary visual cortex, it takes the inputs about those lines and it applies new filters. And again, the filters are all over, the filters are kind of the same everywhere. But they take those lines and they turn them into like kind of, you end up with cells that recognize lines at particular orientations, that pull those particular orientations out of all the information of all the orientations, for example. But you know, it's not too important that we need to understand the particulars of the visual system here. The important thing to consider is that what the visual system is doing is basically applying filters to every portion of your visual input in many layers as you go. And I think the way to think about these kernels is that they're basically, the kernel is basically a filter. It's a filter, and we line it up with this part of the visual input, or in our case, an input image, and we see how the filter changes the input here. And then we slide it over. And you know, we do this one at a time in my kind of demonstration. In the visual system, it all happens at once. All the filters across your visual system operate on the input simultaneously. And conceptually, all these different positionings of the kernel image are sort of like a different filter that have the same characteristics. They just have a different location in the visual input. Am I making much sense? Are people following me? Okay. Okay, good. I'm not super confident that I'm making sense, but it seems like you guys are all nodding along at least. Okay. Stop there. All right. So, okay, I've got my introduction to Pytorch module open here. And I think if we have time, I'll try to update our neural network to include some convolutions, although I'm not confident in my ability to do that on the fly with the amount of time we have left, but we'll see. So in convolutional neural networks, typically, the way that you typically organize them is you start out with some input image. So let's just continue with the example we were working on the other day, where we have these input images of clothing. These images are very small, they're 28 by 28, but let's suppose they were higher resolution and they were normal images. They were RGB and not just these one layer images. So supposing we have images that are like 1,000 by 1,000 and that have RG and B channels. The way the convolutional neural network would typically be set up is that it would have some filters that were pretty small, usually just like 3 by 3 pixels or maybe 7 by 7 pixels. And you would space them instead of having them be at every position like we were showing, you would have them be at every other position, so that when you produce the output of the convolution, you end up with a smaller image. Does that make sense? Why that would work? Yeah, this essentially, if you have a kernel and you line it up with every pixel in the input image, you get out a value for every pixel in the input image. But if you line it up with every other pixel, you get out a value for every other pixel. Nonetheless, you're still going to sum over all those other pixels. They just won't be at the center of the filter. So why would we want to do that? Why do we want to downsample our image as part of the convolution? Well, typically what convolutional neural networks would do is they'll downsample the image in terms of space, but they'll add more image channels. So after one of these convolutions, you'll take your 1,000 by 1,000 image that has RG and B channels, and you'll make it a 500 by 500 image, but it'll have like 50 channels. And those channels don't correspond to colors. They correspond to some kind of data that the filters are extracting from the image. And then we'll apply another convolutional layer that's the same, and it'll make the image even smaller. And we'll have a 250 by 250 image that has like 100 image channels. And we'll keep doing that until we basically just have one image channel and like one pixel of an image and like 1,000 channels. And we'll then take those channels and recombine them into some kind of output. And a lot of times people call those channels something like a context vector. The idea is that you take information that's spread out all over the image and you slowly filter it down so that your information is denser, but your image is smaller, kind of conceptually. That's how, in particular, there's a famous kind of convolutional neural network called a ResNet. Some of you might have heard of it. There's actually a bunch of different ResNets that are different shapes and sizes, but what I've just described is the traditional ResNet architecture, where you downsample and downsample until you have a lot of information density, but not a lot of size in the image. Okay, so I'm going to see if I can. How much time do we have? Still got like 20 minutes. Okay, so any questions about any of that? This is all a little bit high level, so I realize it may not be. If what you're hoping for is like a clear way to implement this, I'm going to make an attempt, but like I said, I'm not super confident. Yeah. Sorry, I couldn't hear the end of that. Would you said something about school buses? Can you? Yeah, so that's a good question. So for people on Zoom, she was pointing out that these neural networks perform really well on like benchmark data sets and stuff, but they learn things like school buses are yellow, and that's how they're part of how they identify school buses. So then would they need to be retrained if you had an image data set from a country where school buses weren't yellow or something like that, or if we went and repainted all the school buses tomorrow, would we need to retrain the network? The answer is probably yes, but note that it's probably yes, because generally we don't know what a convolutional neural network is picking up on. So it's a pretty good hypothesis that if you change the color of a school bus, that's going to be enough of a change to fool a network. But it would depend on the network and how you trained it. So I think that's probably correct in almost every case, but in theory, it might not come out that way. Okay, so we have some people trickling in. So we're already talking a little about Pytorch. I did a little demo of what image convolution was, and apologies if you missed it. It's a little, well, I'll just redo it really quickly for people who are arriving now. Oops. So we already went over this, so I'm just going to be very fast about it. But for people who are just arriving, oh no. Okay. And image convolution is the basic operation behind convolutional neural networks. And here I've drawn two example images. Let me get rid of some of this stuff. These are just simple one channel images that just have 1 zeros and negative ones in them. So they're not like traditional visual images or anything, but the idea behind the convolution operator is that you have a smaller matrix, usually called the kernel, which is the convolution kernel. And this is the matrix whose values are like the parameters that are being learned by the system during the training. And the idea behind image convolution is that you take that kernel, you line it up with some point on your image, and you take the dot product of all the values in the kernel and the values in the image that it overlaps. So in this case, the left and right rows of the blue kernel image are 0, and the top and the bottom, columns of the blue kernel images are 0, and the top and the bottom rows of the gray background image are 0. So the total sum of the product at this point is just 1. And then we would just slide this over and redo the calculation. And then we slide it over and redo the calculation. And we eventually go all the way across the image, kind of in theory, iteratively, although part of the reason, I didn't mention this, but part of the reason we use these calculations in convolutional neural networks and not something else is because you can very efficiently implement this convolution operator using some very clever math and the discrete Fourier transform. And so these operations, even though it seems like these should be very slow, they're actually really fast. You can perform these convolutions really quickly. So if you perform a convolution on an image using a kernel and you line the kernel up with every pixel in the image, you'll get out an image the same size. But often what we do with convolutional networks is, with convolutional neural networks is we line the kernel, we use a kernel that's maybe 7 by 7 pixels, and we line it up with every other pixel. And what that does is gives us a downsampled version of the original input image. And what a lot of neural networks, convolutional neural networks do, for example, ResNets, which are a class of convolutional neural networks that are quite powerful and popular, what they do is they downsample the image in space so that you get a smaller, like a half size image in terms of width and height every time you do a convolution, but you add more image channels. So you end up with a smaller but denser information kind of in your image as you perform the convolution operators. And at the output, you typically have just 1 by 1 pixel image, but you have like 1,000 image channels. So you've taken all this information that's spread out over space and you've condensed it down using these convolution operators into a very long kind of context vector. Okay, questions so far? All right, I hope that was enough of a catch up for everyone who just arrived. Okay, so let's see how to proceed here. So those ResNets, by the way, are typically used for image classification, where you've got like a picture and you want to figure out what's in the picture. This is a good example of the kind of problems they're really good at. If you've ever seen those videos of people at Google taking like a camera around and pointing it at things, and like the screen on the end of the camera just has a little text description of whatever you point the camera at, that's a ResNet probably. That's a network where you take the visual input and you condense it down to the sum long tensor, and then you put that through some natural language model, and it spits out some description of what's there. Okay, so I was saying I'm gonna make an attempt to add a convolutional neural network layer into our network example or our previous example with the clothing. I was saying earlier that I am not super confident in my ability to do this on the fly, so we'll see how it goes. But I believe that the operator we're going to want to use, so down here we use nn.linear, which is a linear, it's basically a linear neural network operation where it takes the 28 by 28 input pixels and spits out 512 output values. I think what we want to use is called nn.conv2d. Oh, of course, I need to reinitialize everything in this notebook because I just opened it. Most of this does not need to be run though. Let me re-download the data. Okay. Okay, so I'm just going to get some help on this because, you know, I've used this before, but I don't have all of Pytorch's API memorized. So, okay, so what the conv2d operator wants to know is how many input channels you have and how many output channels you want. And I believe that the way it works is it trains a different convolution kernel for each output that you want. So we're going to have just a 1 channel input because these fashion images are all just black and white pixels. They're just 1 layer in the image. So we'll have 1 input channel. And I would say we probably want to use something like a 7 by 7 kernel and use what's called a stride of 2. So the stride is how many pixels we skip when we move the kernel over. So if we have a stride of 1, then we move it over 1 pixel at a time. If we have a stride of 2, we move it over 2 pixels at a time. So if we use a 7x7 kernel and we have a stride of 2, we'll downsample the image. Does that make sense to people? Okay, so let's go ahead and try doing this. Oh boy, a lot of information on conv2d. Now, we aren't going to need to flatten the image because convolution works on actual images, not vectors. So this is no longer a needed part of our new convolutional neural network. So I'm just going to comment that out. And I'm also going to comment it out down here because we're not going to need to flatten the image. Now, I'm going to change this to conv2d. And you notice that conv2d didn't care how big our image was. It doesn't need to know the size of the image. It actually will work over any size of image we give it. It just needs to know how many input and output channels there are, because it needs to know how many input or how many layers the kernel needs to have, and it needs to know how many kernels it needs for the output layers. So we're just going to say the input channel numbers is 1. And I'm going to say, let's start by producing, I don't know, 32 output channels. That may seem like a lot, but honestly, that's kind of how these convolutional networks work, is they generate a whole bunch of channels in the interim. And then we'll do a rectification linear unit. That's totally fine. I think that'll work. And then let's go ahead and add another conv2d. Oh, and I forgot. I mentioned we're going to use a what was the argument? Kernel size of 7 and a stride of 2. Okay. And then so we'll do the rectified linear unit, and then we'll do another conv2d. This time our inputs have 32 channels because that's what we outputted here. And let's go ahead and double that and make it 64 channels. And we'll do the same thing to downsample it again. And then I'm basically gonna just copy this line here and repeat it over here. And this will be 64 and 128. Okay, so each time we do this, I believe we're going to downsample it by half. So it'll be half the width and half the height. So after this first operator, it'll be 14 by 14, then 7 by 7, and probably then 3 by 3. I'm actually not, off the top of my head, I'm not sure how it handles the downsampling precisely, so it may end up being a little bit different than what I just said. So now all this said, after that last 2D convolution, we have a lot of image channels, and we still have a few pixels wide and a few pixels tall. So this would be a good point to maybe flatten them. So here we can add the mn.flatten. So that'll flatten our giant image tensor into just a long vector. And then I'd say let's do, as our last step, we'll do a linear reevaluation or a linear transformation into our 10-item vector. And the problem here is that I need to know, I think it's going to be 128 times 3 times 3 values, but we may need to adjust that. And then we're going to want to output 10 values, and those 10 values will be the 10 label categories. So what we're doing here is we're applying 3 convolution operators that make the image quite a bit smaller, but quite a bit deeper. And then we take all of the numbers it produces, we flatten them into a very long vector, and have one set of linear weights that turn that into a 10-dimensional vector, which is our output. Does that make sense to people? Okay. So, I mean, we're going to find out if this works. So I'll go ahead and use the same loss function and the same optimizer. And I'm guessing we'll get an error. Train data loaders. Okay, so I forgot to load my data loader. Oh, it's down here. Okay. try that again. Delete this cell so we don't have to scroll past it. Okay, so I'm guessing we have an error about the size not matching correctly. Okay, so okay, so we did a convolution of a 7x7 kernel on a 3x3 input. So my guess is that we did here. So let's just make that kernel size 2. And actually, if we're already down to a 3x3 input here, maybe the thing to do is actually just to skip this convolution, and we'll do 3x3 by 64. That might be easier. So here's our network. We'll do one convolution, another convolution, then we'll flatten and do the linear recombination. So let's rerun these. Okay, so it's running now, and it does look like the loss is going down. And in fact, it's probably going down a little faster than it was in our previous example. And that's honestly because this is a much more powerful neural network. There's way more parameters in this network. Those convolutions can be a lot of parameters, and that linear, I mean, we created a lot more values in our intermediate layers. So in our original network, we went from approximately 500 values, 28 by 28, to 512. And then we had another 512 values, and then we went to 10. For this, we're creating something like 128 times 3 by 3, or whatever it is, 64 by 3 by 3, and 32 by 14 by 14 or whatever. So there's quite a few more parameters in the middle of this network. So let's see how it did. Oh, I haven't defined NumPy. Oops, NumPy as NP. Okay, we got another error. Two shapes cannot be multiplied. So something is coming out the wrong shape. That may be, did I possibly put the wrong number in our outputs? This was originally a 10 in the first one, wasn't it? Or was it an 11? Anyone have the original notebook open? I just want to check because we need to get that final number correct, or it won't work. Check. Okay. Nope. Another runtime error, but this might help me. Yeah, okay, I know what we did. I think this output value has to be 9. Okay, so let's try training this one more time. 9 is out of bounds. Sorry? Yeah, so I thought it was right the first time. Yeah, so these are our labels. So there's 10, so it should be 10. Okay, so maybe the error wasn't what I thought. Let's try this. Try this again. And while that trains, I'm gonna look at this and see if something pops out. Okay. So it may actually be that we have the wrong. I mentioned that there may be issues with us getting the right sizes of the images after these convolution steps, and I think that might be what's going on here. So it looks like we're having a mismatch between sizes of 64 by 9 which strikes me as being 64 by times 3 times 3, which is the value we have here. And, maybe I think I know what it is. I suspect that what is going on is that this flatten operator only flattens one dimension. That's my hunch right now, but okay. If that ends up working, great. Okay, wasn't just that. All right, well, we're going to see how much time we have here. Okay, we're about out of time. So like I said, I wasn't totally confident I'd be able to get this working on the fly. I think it's very close to working. I just think we've got some size mismatch in here that's not totally clear. And so my intuition. Okay, so I think one more thing we can try here is separating these out so we can print an error message. So I'm going to print the shape of the logits so we have a better sense of what's going on there. And then okay, so now when we start training, it's going to produce a lot of output, but it will tell us something. Okay, 64 by 64 by 3 by 3. So recall that 64 is the batch size, this first 64, because that's how these sizes always come out. To interrupt this. This is the number of image channels, and then it's 3 by 3. So we do have the right size coming out of this linear ReLU stack. The question is why that didn't work. Let me just check my notes here from the old. Well, I think what's happening is either this flatten isn't working right. Maybe we have the wrong argument there. But okay, start dim and end dim. Okay, I think that might actually be it. So if we want to flatten the whole thing. Okay, so I think maybe if we change that flatten to flatten 0 to 2, if this doesn't work, I'm going to give it up and I'll post in the Slack if I manage to get it to work later. Okay, well, we have some shape mismatch lying in our data somewhere that I'm not quite sure I understand offhand. Like I said, I was only ever slightly optimistic that I would get this to work on the fly. But I'll do my best to figure out what happened here and post in the Slack later the correction. My guess is that once we get this working, the convolutional neural network will do a much better job of predicting than the linear network, because like I said, it has a lot more predictive power or a lot more parameters it can use to learn from. But I think the kind of important take home here is that with the exception of understanding these fine details of the inputs and outputs and their shapes, it's actually pretty simple to make a convolutional neural network used in Pytorch. You just have to add these convolutional layers to your network and make sure you understand how they're transforming the image. But I think I'll go ahead and end here. It's already a little past 5. I'd be happy to take any questions if people have more questions or want to see something else. But otherwise, thanks for coming, and yeah, have a great weekend.